The problem on the board is the problem that we ended class with last time. So I'm going to move on unless there are any questions. No questions? Okay. All right, so we talked last time about the cross product, right? And we have another nice result with the cross product. Last time we said that if you take two vectors, let me get my vectors ready here. If you take two vectors, non-zero vectors, you take their cross product, and what do you get if you take their cross product? Another vector, and that vector is perpendicular or orthogonal to both of these vectors, yes? The length of this vector is equivalent to what geometrically? The area of the parallelogram formed by these two vectors, right? So two vectors, we can find the area of the parallelogram formed by those two vectors using the magnitude of the cross product. This formula allows us to find the volume of the parallelepiped. That's what we call a three-dimensional parallelogram. It's called a parallelepiped. We can find its volume by having three vectors. So let me try and illustrate this with my really bad vectors here. I have three vectors, okay? So here's two, right? These two lie in some plane, yes? If I have two vectors, I attach them tail to tail, they form a plane, like a flat sheet of paper, yes? If I give you a third vector that does not lie in that plane, then they will form a parallelepiped. That's hard to visualize, so let me try my best to show you with this thing. I think that's probably good. Do you all see three vectors? Red, black, and blue. Do you see it? Those three vectors, if I extend them, I get parallelograms, don't I? So like this black one and this red one, those two form this parallelogram right here, don't they? The blue one and the red one form this parallelogram. And then the black one and the blue one form this one. And if we kind of take like this face and we just kind of extend it through, we get this solid, don't we? The volume of that solid can be found using this formula. It is the absolute value of the dot product of U with the cross product of V and W. Does not matter what order you do this in. You have three vectors. You just call one of them U. You call one of them V. Call one of them W. You cross V and W. When you cross two vectors, you get a what? A vector. Okay. You take U and you dot it with that vector. When you dot two vectors, you get a number. You take the absolute value. That's the volume of this. It's not a box, right? We call it a parallelepiped. It's called the triple scalar product, or triple product. So find the volume of this parallelepiped that is formed with these three vectors. So we'll move quickly through this. You have to first label these. I'll call that one U, call this one V, call this one W. So what would you like to do first? Cross them? Cross the V and W? So here's V, and here's W. If I cross these, I wrote them vertically so I could do the little cross thing that I did in class last time. So I'm going to cover up what? To do my cross, I'm going to cover what here? The I components, right? And then do the little determinant here. So what would you get? What would you get there? 5, take away positive 1, so 4. Okay, that one's dead. And then cover up the J components. -2, take away -1, which means add 1. So -2 plus 1 is -1, but then change the sign. So 1. And then cover this up. 2, take away 5, -3. Do you all agree with that? Yes? Okay, so remember what I'm doing here. I'm doing the volume is equal to the absolute value of U dotted with V cross W. Why am I saying absolute value and not magnitude? Because this is a number, isn't it? All this in here is a number. So I guess you could say magnitude of a number. That's okay, but all right, so U, I'm going to take the absolute value of U, which is 146, and I'm going to dot that with this vector, 4, 1, -3. And dot products are pretty simple, right? Just components multiplied and then add them all up. So what should we get here? Four plus 4 minus 18, which is -10, and then the magnitude or absolute value of that is 10. So it would be 10 units, whatever we're measuring in. 10 cubic feet, 10 cubic miles, doesn't matter. Okay? This is all still pretty straightforward. There's nothing special here. Yeah, I can't think of anything else out of this. If I would have done this backwards, right? In other words, done this one on top, that one on the bottom, what would the difference here be? These would be negative, negative, positive, right? And that wouldn't have an impact over here because all it's going to do is change the signs here, and then I'm going to take an absolute value. It's not going to have any effect on it. All right, move on. All right, so here's an application of the cross product, something that you run across in physics called torque. Any of you used a torque wrench before, right? You set it and then you turn, you tighten, it clicks, and it lets you know that that's the proper torque for that bolt, right? Or you go to like some tire shop, I won't say where, and they just get the impact wrench on it and over torque everything. And then you wonder when you're taking it off why the actual, bolt snaps because you can't get no, okay, I'm sorry. Apparently I'm not over that. All right, so if we tighten a bolt by applying a force to a wrench, then we produce a turning effect. Torque is a vector which represents the tendency of the bolt to turn. Torque is defined to be a vector equals, what is this, tau? Okay, so it doesn't look like the Greek letter there, but that's tau. The vector tau equals the vector r crossed with the vector f, where r is the position vector of the rigid body, the wrench. It's the wrench, and f is the force acting on the wrench. The direction of the torque vector is determined by the right-hand rule. So remember right-hand rule, right? When you cross two vectors, right? When you cross two vectors, if I cross u vector with v vector, so if I cross this one with this one, the cross product comes out, right? Out of these. If I do it the other way and cross this one with this one, then I have to turn my hand over and it would go in that way, right? So it works the same way with torque. Further, the magnitude of the torque, okay, the magnitude, the length of that vector, would then be the length of the cross product, right? But the length of the cross product, we saw from last class through a theorem, is the length of r vector times the length of f vector times sine of the angle between them. So now I'm going to give you a graphical representation of what's happening. And it's not fitting on here because it's too big. So let me try and make this a little smaller. There we go. Okay, so on the left, what we have is a wrench which is this black one, right? That's my wrench. And I'm going to come and I'm going to apply a force to the end of that wrench, all right? So I'm going to apply a force to the end of the wrench. I could apply that force perpendicular to the wrench, which would be like this, which is what you try and do when you turn a wrench, right? You try and run your force perpendicular to the wrench. You don't ever do this, do you? Put a wrench and you're trying to tighten the bolt and you just grab the end of it and start pulling on it, right? That's not what you do. So, but I could come in at a slight angle if I want. And so what over here is showing you is the torque vector. So it's three-dimensional. If I turn, oh, can I not turn this? Oh yeah, I can't do anything with that, sorry. The way that this works. So this is supposed to be like if you look down, you can see the torque going into the page, right? So it's like the torque vector is going in, yes? So as I turn this, the torque gets bigger. So what happens if I extend, I make my force vector longer? The torque's going to get greater, right? So look at that blue vector. It's going to go down. If I don't put as much force, then it's going to get smaller. What if I run 90 degrees? That's when I'm going to get the greatest torque. How do we know that for sure? How do we know I'm going to get the greatest torque if I run 90 degrees to it? Because it just makes sense, or? That's right, because if you look at the definition, the magnitude of the torque, right, is the magnitude of R, times the magnitude of F, times sine of the angle between the two vectors. The magnitude of R, if we assume the wrench is not going to change length, right? And we assume that our force that we apply is going to be constant, these two aren't going to change. The only thing that actually matters or determines the torque is going to be the angle between them. So we want this to be the biggest it can possibly be. And the biggest that sine can be is 1. And that happens when theta is pi over 2. Yeah? So you want the angle between these to be 90 degrees. You get the greatest torque. And what happens if I take the force vector and I swing it to the other side? Like this? Well, I get 0 here, right? 0 torque. Because what's my angle? What's the angle between the vectors there? 0, sine of 0, 0, so no torque. You're pulling on the end of the wrench and hopefully getting fired shortly thereafter. Okay. And then if I bring it up this way, right, then what's happening? Right-hand rule. The torque is now in the opposite direction. So now you're loosening the bolt, as long as it's a right-hand thread, right? All right, that's just an application. Shows you, how we use cross products. There's the homework. That's it for that. We're going to move on to 10.5. And this is where I told you things will start getting interesting, right? I did, right?
Yeah.
I have all the homework done up through 10.7, so I'm trying to stay ahead here. Finished off 10.7 this morning. 10.5, equations of lines and planes. Equations of lines, hey, we've done this, haven't we? I mean, you were in college algebra and we did that. That was a good old equation of a line. We were happy about that. Not here, okay? This is not what we're looking at today. And planes, do we know what the equation of a plane is? Have you all ever seen the equation of a plane before? Back in college algebra? Something like that. I know in linear algebra you're talking about that, right? Those are planes. I'm saying yes. I'm looking at you, yes. Right? This is the equation of a plane. It's 3 variables, x, y, z. They're all linear, meaning they're all raised to the first power, equals a constant, like that. If you were to graph this three-dimensionally, you would get a plane. Let's just verify it, that we would. You might see me drawing three-dimensional space like that. Is that okay if I draw it like that? Okay. Let's just find some points that live on this plane. How about letting z and y be 0? What would x be? 10? So that would be a point that lives on the x-axis out here at 10, wouldn't it? Here's 5, here's 10, yeah? How about if I let x and y be 0? What would z be? 10, that's another point on the plane? up here. Okay? And then what if I let x and z be 0? What would y be? 3.333, so something like this? Close enough? We good? If you have 3 distinct points, those define a plane, don't they? So we can imagine almost like a triangle between these. And that triangle extended out in every direction would be a plane, a sheet of paper. I brought a plane with me today. There you go. It's a plane. So 3 points, you have a plane, yeah? 3 distinct points. And back in college algebra, we knew that you needed 2 points for a line. We still know that, right? 2 points, distinct, you got a line. All right, that's just to get you to remember. So that's what plane looks like. We're going to look at both of those, lines and planes, today. So let's take a look first at a line. So first, some preliminary concepts. If you're given 2 vectors, we're going to call this R0 or R0 and call this R1. So someone gives you 2 vectors. If you're asked to compute R1 minus R0, the resultant vector is equal to a vector from the tip of R0 to the tip of R1. So instead of drawing in class, I'm about to draw it for you. Okay, here is a vector R1. And I'm going to come in here with another vector R2. Doesn't matter where I draw it, right? I can slide it tail to tail. Or not. There are 2 vectors, yeah? So what is R1 minus R0? Well, that's the same as going R1, right? And then looking at negative R0. Negative R0 would be this, right? And if I add R1 to negative R0, I can slide this up and go the tail of this one to the tip of that one, right? So I do that, I come up here. Okay, that's negative R0. So notice that the resultant vector, all right, the resultant vector goes from here to here. You all see that? That's the result. This is R1 minus R0. You all following me? You all are all looking at it? Yes? Okay. This says that if I take 2 vectors and I compute R1 minus R0, the resultant vector is equivalent to a vector from the tip of R0. Where's the tip of R0? Right there. To where? The tip of R1, which is there. So if I draw this vector, and it's not a very good, I didn't do a good drawing, do you agree that these 2 red ones are the same? Yes? That's what I'm trying to get at. If you subtract 2 vectors, okay, if you take R1, you subtract R0, the answer is just a vector that goes from the tip of R0 to the tip of R1. That's what you get. We're good? Okay. We need that to move on. All right, so now let's look at a line. See the blue line? Now we know that when we talk about lines and vectors, they're completely different things, right? Points and vectors, they're different things. But let's just take a look at different points on here. Every single point that lives on this line has a vector that goes from the origin to it, right? This is one specific vector that goes from the origin to that point. So that point on this line corresponds to this vector, yes? Let me draw some more vectors. All of the points on this line have some vector that corresponds to it, yeah? So if I can find a way of generating all of these vectors, then I'm basically going to generate the line, aren't I? And so what I'm going to try and come up with now is a way of generating all those vectors. That's what I'm going to try and do. Now, how many are there? Infinitely many, right? So it's going to be some sort of function that I'm going to have that's going to be able to draw all those vectors. So that's what I say here. The vector equation of a line is an equation which generates all the vectors from the origin to every point on the line. There's infinitely many. So is this a vector equation? Well, I don't see any angle brackets anywhere, do you? I don't see any vector notation at all. This is the equation of a line from college algebra. We are now looking for what's called a vector equation. It's going to draw vectors. It's going to create vectors. And here's how we're going to do it. So let's say we have a line. First of all, I have some point that lives on that line, right? So any point. Just pick some point on that line. And do you agree that if I know what that point is, if I know what it is, then I can always generate a vector that goes from the origin to that point? For example, if that point was the point 2, 3, 5, right? Let's say in three-dimensional space, instead of on a flat sheet of paper. If that's what that point was, then wouldn't the vector 2, 3, 5 point to that point from the origin? Yeah? Okay. So if I have a point on the line, oh, I did it in two-dimensional space. I better stick to 2D. Right? So if this is a point on the line, then obviously the vector x naught, y naught is a vector which points to it. We'll call that r naught. Then what I want to do is pick another point on the line, x1, y1, and draw the vector that goes to it. Okay? Now, I'm going to subtract the two. So I'm going to do now r1 minus r naught. And what did we say r1 minus r naught really comes down to at the end of the day? When you subtract this, it's a new vector that goes from tip of r naught to the tip of r1. So it should be from here to here, right? Now this is it drawn out. This is what's happening. It's this vector. But I'm about to slide it up. So are we still good with that? I'm going to call that vector v. That vector is called v. So do you agree with this? This right here I'm calling v, right? So if I add r naught to both sides, I get that. Right? If I add this vector to both sides, I would get this. So the vector v1, do you see in the picture that this vector, I said v1, I meant to say r1. The vector r1 is what you get when you take r naught and add v. So you go tip to tail, yeah? All right. Now check this out. What we knew is r1 was r naught plus v. r naught plus v got us here. But what if instead of doing r naught plus v, I did r naught plus 2v? Where would I be? Well, r naught, here's v. Double v would be twice as far down the road, right? So you'd be here. So I've created another point on the line, right? It's not r1 anymore. It's just some other point on the line, isn't it? Could you create another one? How could you create another one? I could go negative v, right? Oh, shit. All right, it's okay. There. So I had this one over here, right? If I did instead r naught minus v, then that would have been r naught, do the opposite direction. You're down here, you have another point. So now I have 3 points, right? This is working pretty good to get all these points, isn't it? It looks like all I'm doing is taking r naughts and adding to it what? What's that? Multiples of v, right? Multiples of v. In fact, if I were to imagine taking r naught, which is this black vector, and here's v, so that's v. I add them together, I get this vector r. I can scale v. So notice I'm scaling v, and I have a number in front here, 1.5. So this is 1.5 v. If I take all the different multiples of v, then I should be able to get a nice continuous line, shouldn't I? All the different values in front of v, including 0. Because what would happen if I took r naught and I added to it, that's not, 0v. I would just be right there at R0, right? And this is where we get this equation right here. What's happening is we have a vector that's being spit out, right? This vector keeps getting spit out. If I plug in a certain number in front of v, it's going to spit out a different vector. It depends on the number. So right here what we have is R0 is that initial vector, that black vector. I'm going to add to it multiples of v. When I do that, it's going to spit out a new vector, isn't it? That's a new vector. That new vector depends on what? The number I put in front, right? This is my scalar. It depends on what I scale v by. So in other words, the output is a function of t. It's a function of that scaling. Now I could have called t a lot of things. We just like to use t for vector functions. And that is the vector equation of a line. It will look like this. Well, it's right there, so I'm not going to rewrite it. And this is a summary of all of what I just said. The vector equation of a line in R2 is this right here, where t is a scalar. V is what we call the direction of the line, or the direction vector. If R0 is this vector and v is this vector, then this is the way it would look. So you have a two-dimensional vector here. You're adding to it AB. We like to use AB for our direction vector, AB. Those are the components of the vector v. So there's v right there. There's a scalar in front of it. If you put these together, right, when you put these two together, it looks like this. Can I pass this t through this vector? Scale through? That's what scalar multiplication is, isn't it? That would be TA and then TB, wouldn't it? If I multiply this t through. And then if I add two vectors, you just add components, don't you? Put these two together, put those two together, put it into a new vector. So you get x0 plus TA, y0 plus TB. So what does it look like I'm going to need in order to come up with the vector equation of a line? What does it look like I'm going to need? An initial point on the line, right, which I can draw a vector to it. That'll be R0. So someone has to give me a point. And I also have to know what? The direction of the line. Now, in our picture, be careful, make note that the direction of the line is this red vector, okay? That vector might require some work for us to get that vector. But that's the two things you need. A point on the line and a direction vector. You're going to hear me saying that over and over and over in this class. At least for the next day or two. All right, so if we take a look at the general vector equation of a line in two-dimensional space, here's what it looks like. The x component right here, all right, and the y component are given by these two expressions. I could say that the x is equal to this and the y is equal to this. These two are known as the parametric equations of the line. That's what those are called. So you're basically just taking that and setting it equal to x, taking that and setting it equal to y. We call the a and the b, right, in that vector v. We call the a and the b the direction numbers of the line. And lastly, if we take the parametric equations and solve them for t, we get what are called the symmetric equations of the line. So there are three different ways that you could see a line written in this class in two-dimensional space. It's either going to be the vector equation of the line, the parametric equation of the line, or the symmetric equation of the line. So I do want to explain this step right here because that people get a little confused with that. If you go to the parametric equations, which were this, did I put AT or TA? AT? Yeah, let me do it that way, AT. Then both of these equations have t in them, right? Solve this one for t. So let's do that right here. Solve it for t. So how about I move the x naught to the other side? Right? Move the x naught to the other side, and then divide through by a. If I divide through by a, I get an equation for t, right? T is equal to this. If I do the same thing for this one, I'm going to get y minus y naught over b equals t. So same thing. Move the y naught over, divide by b, you would get this. Since this equals t and this equals t, they're equal to each other, aren't they? And that's where the symmetric equation comes from. Any questions on all this? Of course, we have to do examples to start to get comfortable, but any questions on the development of this so far? One of the first handwritten quizzes that I've done in a class like this is asking a student to find the vector equation of the line the day after we have this lecture. The last time I gave that quiz, I think 2 people passed it, and I was blown away. I was blown away. Okay? Everyone in here by next class should be able to find the vector equation of a line if I give you 2 points. You should be able to do it. All right? So if you have questions, let me know. I'm going to do an example, but I got to talk about R3 first. So what about if we extend this into R3? Everything's exactly the same. You just have an additional component. So R naught is now a 3-dimensional vector. The direction vector is also 3-dimensional. So instead of using the vector AB, we're going to add a third component on there, ABC. And then if you rewrite this, R naught plus TV, then distribute through the t and then collect together, you get these 3 component expressions. And then if I let this one be x, this one be y, and this one be z, that would give me my parametric equations. If you solve each of these for t and set them equal to each other, you have the symmetric equations. Do you see it's the same thing? Okay. So you get parametric equations, and there are your symmetric equations. Notice something. In your symmetric equations, when you look at them, right, notice that the denominators, right, are a, b, c. Aren't the denominators, aren't those numbers the direction vector, the components of the direction vector? So sometimes, like if I were looking at this right now and someone said, hey, here's a symmetric equation of the line, I would know the direction it points, wouldn't I? Because I would know what these numbers are just by looking. All right, I think there's an example now. No, there's not. Someone remind me to come back to that, okay? Let's do an example. All right, and do you want to do 2D or 3D? You want to do a 3-dimensional one? Let's do 3D. We'll skip that one. Okay, the points 3, 6, negative 4, and 7, 14, 7 lie on a line. Find the vector equation of the line. Find the parametric equations of this line. Find the symmetric equations of this line. Find where this line intersects the YZ plane. So let's try and get some appreciation for what we're about to do, all right? We have 2 points sitting in 3-dimensional space. You're going to give me a function that's going to draw that line. And then you're actually going to tell me where that line hits the YZ plane. Does that seem like that's quite a bit, I mean, not quite a bit, but does that seem kind of cool that you could do that? Someone just gives you 2 points in space, and I'm able to see where it hits a plane over there? Seem kind of interesting? To me, that seems like that might be hard to do, but it's actually not going to be that hard. All right, so what are the things that we need? So we need what? For the vector equation of a line, you need what? A point, R naught. Well, R naught's going to be a vector, but it's going to come from a point, right? So R naught, this comes from any point on the line. And what else do you need? A direction vector. You need V, a direction. Once you have that, you just plug it in the formula and you're done. So what about R naught? Can anybody give me a point on that line and convert it to a vector? Go ahead. What do you want it to be? 3, 6, negative 4. Yes, absolutely. That'll work. So that is a vector that's going from the origin up to one of the points, yes? Now, what about a direction vector? So what can I do to find a direction vector? Got 2 points sitting there in space. Add them. Get the vector going from one to the other, right? Get the vector connecting these 2 points together. If you can give me the vector connecting these 2 points together, that's a direction vector, isn't it? It lies on the line. So V, in this case, is going to be the vector connecting these points. So I have a vector that goes from this one to this one, or I could go the other way around, right? I could go from this one to this one. Does it matter? It does not matter. Because with a direction vector, imagine again, I have 2 points. This vector, let's say, is pointed to this point, right? If I had it the other way around, then it's still the same direction, right? Direction means, you know, vector, they're parallel, they're equivalent, aren't they? So they're equivalent. That it doesn't matter. When I scale it, right, it's going to go both directions. The t is going to draw it one direction and the other direction. All right, so give me v. Let's go from this one to this one. So what's the direction vector going to be? 4, 8, negative 3. Yes? Everyone good? And that's all we need. We're ready to come up with the vector equation of the line. It is r of t equals r naught plus tv. TV. When I was taking the class where I learned this, the book that we learned out of used, instead of r naught, for some reason they didn't use r naught, they used u instead of r naught. And my professor called it the couch potato formula, because it was r of t equals u plus tv. So like u plus tv is couch potato. I remembered it, but I never forgot the formula. But unfortunately, our book uses r naught, so I'm sticking with their notation. Okay, so r naught is the vector 3, 6, negative 4. And we're adding to that t times v, and v is 4, 8, negative 3. Right? That's what we've got. So let's go ahead and keep going here. This is equal to, pass the t through here, right? Four t, 8t, negative 3t. And then add the two together. And I'm going to put r of t back in front here. R of t equals final version, what? 4t plus 3 or 3t plus 4. Doesn't matter how you do it, right? Or not 3t plus 4, 3 plus 4t. So you could do 4t plus 3. Does not. There's no correct way. It's the same. Okay, you just add the components together and we're done. Now I'm going to add one more thing to this. I'm going to put at the end of this, t is an element of the real numbers. You could also say t is an element of the interval negative infinity to infinity. Or you could say t is bigger than negative infinity, less than infinity. What this means is that I am allowing you to use any t you want in here. In fact, I want you to use all the t's. Because if you let t be every single value it could possibly be, it will draw the whole line, right? If I only let t be one value, it's only going to draw 1 point, right? Well, one vector that goes to 1 point on the line. I want you to have all of them. That's important because remember I told you let's go back and look at that note. Don't let me forget. Because sometimes we don't want to draw the whole line. Sometimes we just want to draw the line segment connecting the 2 points. And so we'll have to restrict this. Do you all agree that if I somehow restrict this, I won't draw the whole line? Okay. All right, so that's part A, right? Part B, find the parametric equations of this line. This part's easy, okay? There's like no math to do here. You just write down x, y, z, and you just write down the 3 component functions right here. They are 3 plus 4t, 6 plus 8t, and negative 4 minus 3t. And we're done. Pardon me? You could use for all t, but I kind of stated that already, so I guess we won't restate it. Check this out, though. I mean, let's try and get some appreciation of what's going on here. What if t is 0? Let's just take a look. If t is 0, 0, 0, 0, where are we? 3, 6, and negative 4. We're right here, aren't we? What if t is 1? Where are we? 7, 14, negative 7. We're here, right? You see, so this right here gives you actual points, doesn't it? This right here would have done the same thing. If t is 0, this would have given you 3, 6, negative 4, but it would have given you the vector, wouldn't it have? Which points to a point, 3, 6, negative 4. If t is 1, then it would have pointed to this one, right? All right, so now the symmetric equations. You get to solve these for t. So solve each of these for t, set them all equal to each other, and you're done. So how about we solve the first one for t? What would you do here? 3 over, right? Negative 3, divide by 4. So we're going to get x minus 3 over 4. Okay, and then what about this one? Bring negative 6, so y minus 6 over 8. And then last, z plus 4 over negative 3. Right? And since that would be solving each of them for t, so that means we can set them all equal to each other. And I will point out again, 4, 8, negative 3, 4, 8, negative 3. And if you go back to the vector equation, the coefficients on t are the direction vector, right? That's the direction of the line. So they're pretty obvious in this. Questions? We've done A, B, C. Where does this line intersect the YZ plane? When x is 0? Okay, so when you're on the YZ plane, the YZ plane here, your x coordinate must be 0. That's the condition, right? Your x must be 0. Pardon me? Okay, so all you're doing is you're going to come back. You can look at the parametric equations, right? You can say, hey, look, I need this to be 0, don't I? I need my x coordinate to be 0. So just replace x with 0 and solve for t. So to hit YZ plane, x must be 0, right? So I take that equation, 0 must equal 3 plus 4t. Solve that, we get negative 3/4 equals t. Agreed? That does not tell me where I hit it, right? That just tells me almost like a clock when I hit it, yeah? So to figure out where it hits, you now have to go back into this and replace all of your t's with negative 3/4. Now I like to do it this way. I like to go back to the vector equation because I like working with the vector equation more than this. So the vector equation was 3 plus 4 times t, but t is negative 3/4. And then 6 plus 8 times negative 3/4. And then negative 4, oh crap, what was it? Minus 3t, which is negative 3/4. Okay, so that's me going into the vector equation, replacing all my t's with negative 3/4. Do I have any questions on where I got t from? All right, so go ahead, and this first one should be 0 or else we screwed up, right? This is 0. And then here, what is that, 2 right here? No. 0. Okay, and then this one, well, I think this is going to be a fraction, isn't it? This is a negative 4, going to add 9/4. 7/4. Negative 7/4. That seem right? So if you look at this as a point, the point 0, 0, negative 7/4, that's where that line hits the YZ plane. We're done. Questions? Would be this point, yes. Yeah, you would not, this would not suffice as being the answer, all right? You could do the vector. I'd be okay with that. But just understand that when you usually we're asking for a point when you're asking for where something intersects. Yeah. All right, let's move on. Let's go back to that note. Now the book has a really good way of making this more complicated than it has to be, okay? They give you some formulas for this. I don't like these formulas, I never have. To me, it's much more straightforward if you look at it this way. So I'm going to draw you a picture. And let me just bring this up. Let's say I'm just trying to draw, someone gives me 2 points on a line. Let's make it three-dimensional. Here's a point, and here's a point. Oh wait, we've been using x naught, right? X naught, y naught, z naught. So there's one point in three-dimensional space. Here's another point in three-dimensional space. Right? 2 points. I want to draw just the line segment between these two. So don't draw me the whole line, just draw those. In fact, I want you to draw it from this point to this point. So I want you to go like almost like there's a direction, like I'm going like from that point on the left to the point on the right. Okay? Here's how I'm going to do it. First thing I'm going to do is I'm going to start at the origin, which is 0, 0, 0. I'm going to draw a vector that goes to here. I'm going to call that R naught. That look familiar? We did that a minute ago. And then the red vector, guess what I'm going to call that one? The vector that goes from here all the way over here. V, okay? Then the vector equation of this line is exactly what we just had. Right? But to just draw this segment, how should I restrict t? What should I restrict t between? So let me help you see this. Or does someone want to? How could you draw just that point? What would you make t to just draw this vector? 0, right? If t was 0, you would just draw that vector right here, R naught, wouldn't you? So I want to start at 0. What if t was 1? Isn't that going to add one of these red ones? And isn't one of those red ones going to take me to where I want to go? So between 0 and 1. What would happen if t was a half? Where would I be? Well, I would go out R naught, right? R naught right here. Plus I would add half of v, which would take me halfway, which would be here. Agreed? So if I take 0, I'm at the left end point, right, of that line segment. If I take 1, I'm at the far right of this. If I take half, I'm halfway. If I take a quarter, I'm a quarter away. 3/4, I'm here. So every number between 0 and 1 is going to help me draw everything in here, yes? That's the idea. Does that make sense? The key to this is the setup of it. If you're going to go from one point to another point, R0 has to be your first point, and V must be the vector from here to here. So we'll do an example. I don't think I have one in my notes. So let's just do a quick one. Find vector equation of line segment from 3, 5, -2 to the point 5, 8, -9. So I'm going to go, I want you to draw this segment that connects these 2 points with the vector function. R0, start with R0. What do you want to use for R0? 3, 5, 2. 3, 5, -2. If you're going to follow the way that I've suggested, do you have a choice? No, you do not. R0 has to be this. R0 has to be the starting point. So it's the vector 3, 5, -2. Then you need a direction vector. Your direction vector, do you have a choice? No, not if you're going to follow this method. It must be the vector that goes from here to here. So you're going to take these and subtract those. So that would be what vector? 2, 3, -7. And so now you have the two things you need, R0 and V. And you've got to write R0 plus TV, which is, now go ahead and put those together. Let's see, is this too much? Am I pushing too far to put them together in my head? Or is that all right with you? It's okay? All right, sir? What's the restriction on T? Just say, I don't know. It's okay to say, I don't know. Okay. Okay. You seemed kind of zoned out, so I wanted to kind of pull you back in here. All right? Okay. What's the restriction on T, everyone? 0 to 1, right? And it's always going to be that way. Guaranteed if you set it up the proper way. All right? T is 0 to 1. Now, how could we quickly check this? Let T be 0? Where should we be if T is 0? Here, right? Is it? Kill these off. 3, 5, -2. Is that where we are? Okay, let T be 1. Oh, yes?
Is it always 0 to 1?
Where? Yes. Yes. It's always 0 to 1, as long as you set this up the way that I suggested. If you've got 2 points you're trying to connect, right? From one point to the other. You have to let the first point be R0. You have to let V be the vector from here to here. If you do it that way, your restriction will always be from 0 to 1. All right? So if I let T be 1, I'm going to be at, what, 5, 8, -9. That puts me here. Any number in between is going to be somewhere in between those 2 points on a straight line, and we're good. Understand? Good? Okay. All right. Moving back to the notes. Example 3. Determine that these lines are skew. That means they do not intersect, they are not parallel, they are not orthogonal. Okay, got a lot of shit to look at here. we have two lines sitting in what dimensional space here? Three-dimensional space. Now these two lines are given to you in a way that you've never really, like this is the first time we've actually worked with lines in a vector format. Okay, so here's the vector equation for the first line. It has three components, right? Here, here, here. And then the second line has three components here, here, here. Now notice though, here we're using t as a variable to draw this line, and here we're using s. Right? The reason is because those are dummy variables. T was like a background, just domain that was just, t was varying between whatever, right? All real numbers. And it doesn't have to correspond with this. Let me see if I can illustrate that better, because I didn't do a good job of that when I was doing the homework solutions either. Look, if I want to draw this line, I just start plugging in values of t, right? It's going to start drawing me points on that line, right? Different values of t. If this was also t, right? If this variable was t, then let's say when I plug in t as 0 here, I get a point on the first line. And when I plug in t as 0 here, I get a point on this line, right? Second line, different line. These two are not really connected to each other. In other words, what's happening at t0 here does not have to be the same as what's happening at t0 here. Like, they're not drawn at the same time, at the same background domain time, if that makes sense. These are independent of each other. So we use two different variables for it. Does that kind of make sense? If we make them both t, then we're saying there's some connection between these two lines. Like, they're drawn at the same time. Like, that point's drawn, this point's drawn, then that one, then this one, then that one, that one. It's not like that. They're just there. They just exist. So we're trying to keep the points separated from each other. All right, so we got line 1, here it is. We've got line 2, it's sitting out there. We need to show us a couple of things. That these lines are skew. That means that they can't hit each other. Okay? They can't be parallel. And they cannot be orthogonal. If they're orthogonal, parallel, or hit each other, then it's not skew. But I'm trying to show you it's skew, so that they're skew. So how do you suggest we go about this? Okay, so what are you going to look at first then? Who said that? Okay. You want the direction vector of each of the lines? Right, this one has its own direction, right? This one has its own direction? And you want to look at both of those? I agree. Because if they're parallel, they should point in the same direction. Or their direction vector should be scalar multiples if they're parallel. If they're orthogonal, then their direction should be what? Perpendicular, which means that the dot product should be 0. Yes? And then intersecting, we'll get to that in a second. All right, so let's take it. Tell me what the direction vector is for this line. And we like to call the direction vector v, didn't we? I'm going to call it v1 because that's for the first line. What is the direction vector of that line? You know what I really want to do, and I've been doing this in my other classes, is I've been asking all my students to fill out these little forms. I did it with my Cal 2 students, and everyone has like their names on these, and you have it on your desk, and I can call on you and learn your names. I might start doing that next time, because I want to be able to like turn around and say, Hector, what's the direction vector of line 1, Hector? You know, and call people out and keep you kind of on your toes a little bit. So yeah, thank you for volunteering. Do you know what the direction vector is for line 1, Hector? Okay. Good. So where are you getting that from, Hector?
From line 1, the component that's next to the t.
Okay, so you're looking at the coefficient of the t,
Yeah.
right? So 1, 3, negative 1. Very good. You're off the hook. Everyone got that? That's the direction in which the line 1 points. How about V2? Hector already gave away the secret. So what's the direction vector for V2? 2, 1, 4. Right? This time it's the coefficients of s, because s is the variable.